So it's a pleasure to have Anushya Milliken. I hope I said your name correctly. He's just graduated from Princeton University. He's moving to Santa Barbara. He'll be telling us about quantum error correction and large N. So please go ahead.
Thank you very much. It's a great pleasure to me to give a talk in Minneapolis. And today my talk will be about quantum error correction and large N. So I will not assume that the audience will have any knowledge in the quantum error correction. And the type of error correction I'm going to talk about is very basic. So I will give all the definitions. So let me just in one slide briefly give you some historical references and motivation. Again, the motivation comes from the fact that in quantum computers, there is noise, so there is a need for error correction. This is one of the motivations. And that motivation is actually related to the holographic correspondence. Again, my talk is motivated by these 2 points, but I will not actually need any knowledge or any facts from the holographic correspondence. It's just a motivation. So in 2014, Almeri, Donk, and Harlow demonstrated that quantum error correction seemed to be tightly related with holography. And this quantum error correction interpretation actually resolved certain tensions, but I will not talk about that. And just on the intuitive level, error correction generally implies that there is a redundancy in data representation. And indeed, all the examples of ADS-CFT correspondence include large gauge groups. The most basic example is SUN super Young-Nielsen 4 dimensions, which is due to 10-dimensional Einstein gravity. And this quasi-classical correspondence works for large N. And indeed, in the gauge theories, we usually concentrate on gauge singlet states. And it was demonstrated by Minton, Palczynski, and Rosenhaus that indeed the singlet states can serve as quantum error correcting code. And this actually pairs well with certain dynamical facts. For example, one can reduce this aforementioned super Young-Mills down to 1 dimension, just to quantum mechanical matrix model. And one can argue that all the nice semi-classical gravity states correspond to gauge singlets, whereas non-singlets are separated by a finite gap. So another point is that symmetry is not always good. In quantum information, Easting-Knill theorem rules out error-correcting codes with continuous symmetry. In my current talk, I will talk about continuous symmetries, but Easting-Knill theorem will not be applicable because of a technical reason. Maybe I will explain throughout the talk why. So this is just historical references and motivation. So specifically in my talk today, I would like to emphasize the importance of large N limit. Namely, large N automatically implies a version of quantum error correction in the gauge singlet sector, regardless of the Hamiltonian. And specifically, I will discuss matrix models. One can think about reduction of Young-Mills theory or so-called tensor models. So these are probably not familiar to most of the people in the audience, so I will also give a brief introduction. So these tensor models, they are interesting because they have the same large N limit as Sachdev-Yakitaev model, but they don't have disorder. So they have a fixed and defined Hamiltonian. Whereas in Sachdev-Yakitaev model, this model contains disorder. So I should say right away numerous disclaimers. First of all, I will consider quantum mechanics of fermions. because I want the Hilbert space to be finite dimensional. So I won't discuss bosons. From the IDS-CFT correspondence, my perspective will be purely from the boundary. I won't do any gravity calculations. And in fact, it was one of my motivations because it seems quite easy to argue from gravitational point of view that there is a version of quantum error correction in IDS-CFT, but I believe there are no field theoretic arguments why it should be the case. So one of my motivations was to fill this gap. And maybe more important thing is that typically the miracle of the holographic correspondence is that some strongly interacting field theories are dual to Einstein gravity, which has a very well-defined geometry. But in my case, I will just talk about generic large N models. And for them, we don't expect that even if the gravity dual exists, that it will be just a nice Einstein gravity. There are expectations that the geometry in those cases will be highly curved. And it was discussed in a series of papers by Bernstein, it's Heike and McGreevy around 2004, that for generic matrix models, one can give a string theory interpretation, but in those cases, strings propagate in a highly curved stringy sized geometry. So I believe that the error correction I'm going to talk about is more applicable to these models rather than the theories with the local bulk dual. So in my
but your theory, it is still you're discussing in terms of local theories, right? Because it depends on dual. You are talking about normal local Lagrangian Hamiltonian, no?
In quantum mechanics, it is not. It's not really clear what we mean by local. Because,
no, okay, but if you believe that it is a kind of a remnant of relativistic local theory, or it's not, just to follow what because you said, for example, quantum mechanics of fermions finite dimensional, okay, but when you apply that finite dimension in field theory, it's infinite dimension, not only because of fermions or boson, but just because you have kind of all this higher states, right? So in this way, Hilbert space is never finite dimensional in this sense. But you mentioned in your disclaimers, so that's why I'm asking.
Yeah, I think at least all studied examples of boundary quantum mechanical models with bulk duals, they are local. At least they are local in time. So they are usually some dimensional reductions, as you said, from higher dimensions.
Okay, yeah, but there is no locality in you mean in relativistic sense, right? Because when you're you see, because no, it always bothers me that say when you have a gravity, then you are saying that the theory can be stopped to be kind of local. Just because of gravity, right? It is the way people are usually formulate this.
Well, it's local above the Planck scale. Yeah.
Yeah. No, but essentially they are saying that in this way, kind of normal kind of operator product expansion. When you are starting with some short distances and going to larger distances, that it doesn't work, right? In quantum gravity.
I'm sorry, quantum mechanics of fermions is just the Hamiltonian is a matrix, right? It depends. For any finite number of fermions, Hamiltonian is just a matrix. What kind of locality can you say?
No, right. But then it's not.
It's just a finite dimensional matrix with finite number of eigenvalues and finite number of eigenstates.
No,
That's it.
Yes,
right,
yes.
right. I agree. But then it's quantum mechanics. Then it's not relativistic theory, right?
Of course, quantum mechanics is quantum mechanics, but okay, maybe some other theories, I don't know this. It has Lagian. Lagian is probably the number of...
No. But even in quantum mechanics, the Hilbert space is not limited by spin degrees of freedom of fermions, right? Because you can have excited states, right? If you consider quantum mechanics of realistic fermions, right?
No, if they are realistic, if they are fermion fields, then of course the question of locality, then you have infinitely many degrees of freedom.
Right.
Of locality. But if it is quantum mechanic, I emphasize quantum mechanic, any finite number of fermion degrees of freedom corresponds to a finite dimensional matrix as a Hamiltonian.
No. Okay, it is a point which I not clear extremely to me, and it's what I'm trying to ask Alexei. That look, if you have a finite matrix, then I would say that it is not only finite number of fermions, but it's also finite number of levels. Because then you are...
Yes,
of course, by definition.
Right, because if it's just finite number of fermions, you still can have higher levels, right? I mean,
yeah. So this is why I'm studying fermions, because if you have just a bosonic harmonic oscillator, then its Hilbert space is infinitely dimensional. You can have an arbitrary excitation number. But for fermions, it's not the case. It's fixed.
Right, but for fermions also, if you consider include also higher states, for normal fermions, you also would have, not a finite matrix, right? Because you still have then higher states as well, right? Even for fermions.
Mm-hmm.
So in this way, if you would say that excitation would not be considered, but just this kind of finite number of levels, then I agree, right? Then you have a finite matrix, right? Or I'm missing something maybe.
Well, let me maybe say it from different perspective. By using Jordan-Wigner transformation, you can always map fermions to spins. And then if you have n spins, your Hilbert space has a fixed dimension. It's 2 to the power of n. And it includes like the ground state and all possible excitations. It's just 2 to the n.
No. But then you are not accounting for any additional momentum states, right? Because you have, of course, you have spin. Say you have one fermion. Okay, how many states? You have 2 states, but in terms of spin. But you have, infinite tower of states in terms of energy excitations, right?
Yeah, but I'm considering. In some sense, it's zero dimensional. The fermions in the spins, they don't move in space.
Right. I agree. Yeah, and that's what I'm trying to say is that in this way there is no momentum, right?
No, there is no momentum.
Yeah. Okay. No, I'm sorry. Just to follow. Sorry to interrupt.
Sorry, can I just ask a quick question?
Yes,
on the stringy geometry, normally when you have large n, it corresponds to strong coupling in the gauge theory. So that's just Einstein-Hilbert gravity in 5D. So why is there stringy geometry then?
I believe so. N it fixes the interaction strength in the bulk, whereas the locality is determined by the 't Hooft constant. So when you send the 't Hooft constant to be large, then the 't Hooft constant is the ratio between the radius of the curvature divided by the string scale. So it's the 't Hooft constant which controls the locality in the bulk, and whether you include higher derivative correction to the Einstein action or not.
But are you taking large 't Hooft coupling though? That's what you're doing, right?
No, not necessarily.
Not necessarily. Okay, fine. Yeah, okay.
So in some sense, yeah, I was gonna say that probably this story it's somewhat orthogonal to what people talk in this semi-classical bulk picture, and quantum error correction, because for them, the bulk locality is very important. Even the name of this original paper by Almeri Donken Harlow is called Bulk Locality and Quantum Error Correction. So for them, the 't Hooft constant was very important. The large 't Hooft constant was very important. But in my case, the large n is important.
I see. Okay, thanks.
Yeah, but returning back to this counting, I would say that when you're saying it is zero dimension, I can formulate it in the following sense: that let's consider normal quantum mechanics of some number of fermions, and then let's consider only what's going on to be from this ground state or nearby. So don't consider any excitations associated with kinetic energy possible, right? Okay, then we are back to this, finite metrics, and we can say that it's like a splitting of original, say, degenerate ground state.
Yeah, you can think about this way, that I want to get rid of all possible momentum excitations.
Yeah.
So
right.
my Hilbert space and all the operators, they're just big matrices.
Yeah.
Presumably exponentially big in n.
Right, but I can say that it's like a splitting of ground state, right? If you neglect interactions, and all states are degenerate, right? Which we have, and then we are saying how we can, accounting for interaction, what would be number of states coming from this? What would be states coming from this degeneracy?
Well, I would not say that it's near the ground state, because you can have an arbitrary complicated fermion configurations. So they might have like big energy too.
Yeah, ground state in terms of minimizing kinetic energies, because you said that there is no kinetic energy, right? So ground state in terms of momentum excitation.
Yeah, but you also have a potential term, and potential term.
Right, but potential term, it is the one which splits originally degenerate states into non-degenerate states. You see, so start from zero interaction, right? You would have just, some number of degenerate states, because all the states would be the same energy. Okay, so modulus reference energy or whatever. I'm not counting from where you count this energy, but in this way, it's like Fermi feeling, at zero interaction. Okay, I'm sorry. Okay. Yeah, no, but no. I believe that we kind of I did understand where we are going.
Yeah. It's important that fermions, they are not moving anywhere. So they are just, you can map them to spins. So I just have these fermions or spins. They don't move anywhere. So they are dimension of the Hilbert space is determined by their number, and it's just a big number, exponentially big in n. And in principle, it's not the singlet states. They don't necessarily close to the vacuum, so they can be quite involved and have high energy. And actually, what's important in this is that I'm going to show that all singlet states, regardless of the energy, have these error correcting properties. So the question I want to address is how robust are the singlet states in these models against errors, such, for example, as erasures.
Would you explain what is erasure, error, or something about errors?
Yeah, I will explain this in maybe in a few slides. Yeah, I'm gonna give all the necessary definitions. So the outline is this. I will just in one slide again remind this holographic motivation, and then essentially illustrate all my claims by a very simple illustration. And then I will discuss what is erasure and what are the quantum error correction and so on. And then apply all this machinery to matrix models and tensor models. So again, this is just one slide about holography, but I won't use it anywhere. But just to give you a flavor, so the holographic correspondence says that we have a field theory, say in one-dimensional boundary. Here it's two-dimensional, but I am drawing just a time slice. So these ABC, they are spatial regions. And then this quantum field theory is dual to gravity in one higher dimensions. So this is two-dimensional disk. And the HKLL bulk reconstruction says that like all the gravity fields in certain region in the bulk can be reconstructed from a certain region in the boundary. So for example, A is dual to KA. So I can say everything about KA just from knowing A, and I don't need anything else. And for example, if I want to reconstruct something around point A, then all I need to know is I need to know A and C, because actually for A and C, this so-called causal wedge is bounded by this KB. So if it's this line, so O lies inside the causal wedge of AC, and the same happens with AB and BC. So in order to reconstruct O, I just need two regions, not three. And so one of the regions might be lost, but everything encoded in O will be intact because I can still reconstruct it. And this actually very similar to quantum error correction. And so it seems that the holographic states are robust. So the loss of A does not prevent us from reconstructing O. So unfortunately, quantum mechanical models, they don't have spatial structure, and there is no geometry, but I can still study the robustness against introducing certain errors. So as I said, everything is finite dimensional from now on. And so this is actually my central slide, and suppose I have some fermions in the adjoint representation of SUN. Okay, so I just have fermionic matrices.
I'm sorry, but in certain sense you have no dimension, right? The way you approach this, right? So yeah. For you, this, I mean, this extra dimension, it would be, you know, I mean, it's not there. Like, original dimension is not there.
No, it is not. But I can still study erasures. I will talk about it in a few slides, and I can introduce like a general errors. Just poke my system with certain operators, and then see if I can remove the action of these operators. I'm gonna illustrate this now. This slide, it will be secretly about certain quantum error correction. So I have these fermionic matrices in the adjoint representation of SUN, and I start from a singlet state, okay? And I add errors or perturbations. You can think about them in both ways. So I just take one of the fermions and just hit my state S with this fermion, this way or that way. So these errors are not singlets, so they have just free adjoint indices. So these states, Xi1 and Xi2. And then the question I'm asking, okay, I know the original state S, and then someone presents me a state in a black box. Can I say for sure which state is that, Xi1 or Xi2?
Excuse me,
I'm allowed to do measurements.
Do you need two flavors, psi and chi, or just one psi with two adjoint indices? With an adjoint index is okay.
Just one adjoint index is okay.
But what means adjoint? So 3-1, it's adjoint indexes, or it's spin notation for adjoint? What is it?
No, this is adjoint. So these indices ij, they run from 1 to n. So these are just
right. So
n by n matrices.
No, right. But so it means that each index, it is like a spinor index, right?
No,
you have.
why?
No, you have
in some abstract space. It's not a spin. Fermion.
No. In terms of just
mechanics. Fermion in quantum mechanics is just matrix, and now there is this matrix.
Wait. We are talking about representation of SUM, right?
Yes.
Yeah.
In representation of SUM, when we say join, this joint representation has n square minus 1.
But at large n, this one is irrelevant. It's n by n matrix.
No. Mish, you are not listening to what I'm asking. Of course, I'm not talking about this minus 1. I'm asking that this n square in terms of psi ij means that each I and each j goes from 1 to n, or other one. If it's from 1 to n, then I'm calling spin notation in terms of each I and j. It is corresponding to a fundamental representation counting of I and j, right? And just checking that ij.
One is fundamental, another is anti-fundamental.
Right. No, I'm just checking this. That in this way, that I and j not adjoint indices in terms of that they are not going to n square, right?
No, this is correct. Yeah, I and j, they both go from 1 to n, and one can think about this, that I is indeed fundamental, and j is anti-fundamental, and these are fundamental, anti-fundamental, these are vector representations.
Right. So when you are acting by psi on singlet, the state psi1 and psi2 are non-singlet, right? They are not singlets.
They are not singlets.
I see. Mm-hmm.
So the question I'm asking, can I distinguish psi1 and psi2? And the fundamental law of quantum mechanics is that I can distinguish them only if they're orthogonal. So if I compute their overlap, so I have very carefully chosen these indices such that I can form a singlet. And I form a singlet because state S is a singlet, so only the singlet channel contributes.
Mm-hmm.
So I contract all these indices and divide by n cube, because this trace, it contains n cube terms. And in general, we don't expect that this matrix element is 0. And we expect very naively that it contains n cube elements. So naively, it's of order 1. But I claim that actually the matrix elements of this operator can be bounded by the power n to the 5/2. So we are saved by square root of n, and it means that this overlap, it's very small. It's of order 1 divided by square root of n. So in the large n limit, these states, they become approximately orthogonal. And it means that I can, at least with high probability, not perfectly, but with high probability, distinguish psi1 and psi2. I'm going to explain in the next slide why this 5/2 comes from. But if you don't believe me, I can just say that specifically this 5/2 this is what you expect in the planar limit. So if your theory admits a planar limit,
I'm sorry,
it could be 5/2.
Psi do not have fermionic number, right? I mean, because if it would be fermionic number, it would be 0 as well, right?
Excuse me?
I'm wondering, that if psi would be with fermionic, having fermionic number, so you mean that each psi is in this way has no fermionic numbers, right? I mean, additional to SUN, right? So because if it would be additional numbers, then psi cube would be, kind of not allowed to be non-zero, right? Because imagine that it is not SUN, but say like UN, right? You have the kind of additional number, and then psi cube would be this number would be 3. Because then you differentiate between psi and psi bar, but you do not have any psi bar, so it's like Majorana type, right?
Yeah.
I see. Okay, sorry.
Can I ask a very naive question about the motivation? So the reason you want to check whether you can detect the errors is because a prerequisite for correcting the errors is knowing that one occurred in the first place. Is that right? Like why do you need to detect these errors?
So for example, well, there could be two motivations. So from quantum information, motivation is that typically such actions, so you can think about this as, for example, as sigma matrices. And then if you act, for example, by sigma z, you have a phase depolarization. So your spin, which is spin down, acquires an additional phase.
Okay, I see.
So it's actually when people in quantum information talk about errors, they actually talk about this kind of very basic spin flips or phase flips.
I see. And the idea is you want to be able to detect such errors so that they can be corrected by some algorithm.
Yeah.
I see. Thank you very much.
Excuse me, may I ask you a stupid question? Let's say we have only one error, not two of them to compare, but only one. Let's say psi2. And it's an Arrhenius signal. In fact, it should be something else, maybe psi21, psi12. Instead, we got psi21, psi32. How do we know from this single signal that it's a wrong signal, an error? How do we know?
So if they are orthogonal, then in principle, it's possible
orthogonal to what? Say you're comparing two erroneous signals, and then you say, okay, these signals, if you take the expectation value over singlet, then they're orthogonal to each other. Now I'm trying to ask something else. Assume that the true signal had been sent psi1 to psi2 1, okay, times singlet, okay. Instead, psi1 2 came in a erroneous way. It became psi3 2 on a way. How do we know that this is an error at all? Or how do we know? The fact that this is a non-singlet, so then you say that only singlet signals can be transmitted. If you obtain a non-singlet, not a Swan singlet, that this is an error by definition, right? That's what you are saying.
I think in what you're proposing, there is you introduce a third state, which is this psi1 to psi2 1. Yeah, so apart from this psi1, psi2, you will also have psi3.
I don't introduce psi1 at all. Let's say I don't introduce, I have psi2 and another psi2, psi3, let us say, which have psi1, 2, psi2, 1 instead. And I would think, if it is actually possible in your model, to make psi3, which I described to you, the signal which I want to transmit your quantum mechanically through a spin or whatever. And now it came, due to an error on the way, it came to us as psi3 2, psi2 1 instead of psi1 2. Just one index changed on the way. It's an error. It happens, right? It happens because nothing is 100% perfect. How would you say, just looking at this and not knowing what you were supposed to obtain instead of this, how would you know that's an error? Would you say it's an error because psi2 is not SUN singlet? That's what you want to say.
I would do this. I will perform a measurement of a Hermitian operator. And then suppose my Hermitian operator gives me +1 if it is some positive signal, -1 some negative signal, and 0 if it is an error. And then I will measure, I will just get this message I will measure this this operator.
No, okay.
And see what I get.
Explain it in this example which you discussed in the line number 3. I don't understand two abstract statements. Here you have a state, you call it psi2, and you are saying, let's say you suspect that it's an erroneous signal which you obtained. Okay, I don't know what Hermitian operator would you use in order to measure that your state in your measurement device appeared psi2, and you expected a different answer. Instead of index 3, subscript 3 here, to have index subscript 1. And instead, because of the error on the way, some error bars or whatever, you get, instead of 1, you get 3. How would you know a priori, without knowing what you were supposed to get, how would you know, you don't have psi1 at all, how would you know that it's an erroneous, it's an error which have to be somehow to discard it, or another request for a signal should be sent? How would you know?
Yeah, this is like, in order to understand this, people do so-called syndrome measurement. So I measure a Hermitian operator, and then—
Which operator in this particular case?
This is a good question. Well, specifically, I can, for example, project onto Xi1 and Xi2.
And where Xi1 comes from? From a different signal. So you have two different signals, okay? And their projection on each other is 0 in the larger limit. What does it tell you? That presumably what you want to say that each of the state here is not color singlet. And then of course the trace would be 0. We know that the traces of not color singlet operators at large n are suppressed by some powers of 1 over n. But then you should say that the only correct signal which you expect to obtain would be color singlet. And then the amount of information is hugely decreased because you disregard all states, multi-level states, you know, which are, although I don't know for fermions multi-level states, it's a little bit a question mark, but you disregard all states which are not singlet, which are presented by states which are not singlet with regard to SUN symmetry, right? Then you leave only SUN singlets. Then the number of states is decreased by 1 over n squared or something. It's just a very limited signal. And then I still would ask, okay, let's build two color singlet states. Their projection onto each other is definitely not suppressed by 1 over n, but they're different. Two different color singlet states. This can be possible. One is built from 2 psi and another build is 4 psi. Both are color singlets. Their projection is not suppressed by 1 over n. Why would you suspect that one signal is correct and the other is wrong? Or both
okay.
may be.
For singlets, it's not possible, yeah, at least in this framework. Here it's important that they are non-singlets, and this is why there is this trick of dividing by an n cube and then bounding the matrix element. Yeah, for singlets, this wouldn't work.
Okay, then compare two non-singlet states. You can say that if both of them are non-singlets, then generally speaking, their projection onto each other will be suppressed by 1 over n. But maybe it means that both of them are wrong and the right signal was meant to be, for instance, a singlet state. How do you know that an error which makes a singlet states, SUN singlet states into SUN non-singlet state is an error and not what you were supposed to get? Unless you only proclaim or state from the very beginning that every state can only be the true signal if it is color singlet. But then
yeah.
you source out from your Hilbert space a huge amount of states, leaving only a very small corner as a possible candidate for the SUN singlet states. But even in this case, I still am entitled to ask a question. If you have two color singlet signals, but one of them somehow is erroneous, something on the way happened that one color singlet changed to another color singlet, and one of them is due to an error. You compare two color signals. They have an vanishing projection on each other, but maybe one of them is still an error. What would you say about this?
Yeah, in this case, if an error is a singlet, yeah, I cannot say anything. So this.
Okay, so it's not a true error correction program then, not a true error code, because you say, okay, I'm having a huge number of states in my Hilbert state. Some of them are color singlets, of which you can say nothing, but you can say something of color non-singlet signals, provided that you have two of them, and then you can say immediately, but if one of them, let's say one of them S, and another is color non-singlet, you will also have a 0, right?
Yeah.
Let's say your Xi1 is just S, and you sandwich Xi1 and Xi2, because this is not color singlet, and the sandwich between two color singlets, you will get 0. So, of course, in this way, you will be able to distinguish a color non-singlet result from color singlet result. Which of these results is correct and which is wrong, you cannot say unless you postulate that the correct result is color singlet only. And then the question of error correction reappears in the form, you got two color singlet results. How do you distinguish if one of them is erroneous result? How can you say that it's erroneous in your method?
Yeah, as I was saying, for if errors are singlets, I cannot say anything. But here it's the fact that I can distinguish two non-singlet errors. It's already good because
why do you know that both of them are errors? Maybe one is error. Maybe the second one is what exactly was meant to be received. And in the first one, okay, the first psi got erased somehow on the way. It's possible.
I want to reconstruct S. And so this is why I need to know which errors occurred. Because if I don't know which errors occurred, I cannot remove them.
Okay, then this just confirms what I said. You only can do something if you postulate that the correct result is color singlet, and then you can distinguish color singlet from color non-singlet because the overlap would be 1 over n. That's certainly true, okay? But then, of course, the same question, as I said, reappears in the sector of all possible color singlet results because it's very large too. Not as large as all states in the Hilbert space, but at large n, it's still very large. It's probably of order n. I don't know how large. It depends on how many. Okay, you have n squared different size, so up to n squared different signals can be obtained, which are still color singlets, right?
Mm-hmm.
Or maybe n squared.
Yeah, when people talk about quantum error correction, typically you fix what are the errors and what are the signal, because if you say that you can correct everything, it means that you can correct the signal as well, which means that you cannot really transmit anything. So here I'm saying that the signal is a singlet and errors are non-singlets. And in order to remove errors, I need to distinguish between them. It is not that state S should be orthogonal to non-singlets. It's trivial. What is important is that Xi1 is orthogonal to Xi2 because when I get some state in a black box, I perform a measurement.
The first one is error, in the second signal is error too, right?
Yeah, but I don't know which error it is. This is the point. It comes in a black box. And the black box does not have a label, whether it's Xi1 or Xi2. I need to determine that.
Okay, so you are saying that any true signal should be color singlet.
Mhm.
Then I agree with you. If every correct signal should be color singlet, and all color signets present a correct message, which is also not, you know, because you might have originally a non-color singlet due to an error in one index here, which is always possible because the quantum mechanics is not double valued. Each index here can be, because it's quantum mechanical, it can be accidentally put 3, and in fact it is 1. And then you can still build a color singlet, or it's a part of color singlet, but okay, a small part of color singlet. But you say if you have just something which is a small part of color singlet, mostly it's color non-singlet, this goes into trash box, right?
Not necessarily, no. The point is that I can correct them. Suppose I somehow performed a measurement and I realize that, okay, it's Xi1. Then I will just act with Psi3 again. So these guys, they square to 1 as Majorana fermions. And then I will recover my original state. And I performed the error correcting procedure.
What is, excuse me, can you repeat? You got this Psi1 as a single, then what do you do in order to?
I act on it with this operator Psi3.
Yes.
And, apart from some 1/n things, it squares to 1. So if I act with Psi3 again on Xi1, I will recover S. I will recover the signal.
Why Psi3 squares to 1?
Psi3 squared implies to be 1, right? Yeah, it is like a square of fermionic operator. I mean, like sigma square.
Yeah.
No, but normally for fermion operator, if it is just 1, psi squared is equal to 0 because of anti-commutation, right?
No. It's equal to 1 for fermion, right?
Yes.
No,
yeah.
Fermion
like,
is the same as sigma.
Yeah, precisely. This is the point.
Sigma anti-commute, right? It's fermion.
Yes. Yeah.
And sigma square is equal to 1.
Yes.
If anything, something anti-commute, sigma is anti-commuting variable, and sigma times sigma equal to 0.
No, sigma times sigma equal to 1 if it's the same sigma. Come on.
Why? For anti-commuting variables?
Yeah, for anti-commuting variables, right.
Sigma times sigma is equal to minus sigma times sigma.
No, so sigma times sigma 1 square equal to 1. Sigma 2 square equal to 1.
That's true.
No, that's it.
But sigma 1 commutes with sigma 1. It's not anti-commutes. Of course,
this is the correct anti-commutation relation. So this is the anti-commutation relation of Majorana fermions. They anti-commute.
When you quantize it, it becomes sigma. Look, Mish, you know this very well. Look, you start from the fermion. When you quantize it, psi becomes sigma. But it's a realization of.
That's because Majoranas are only defined through Diracs. Then psi is sigma plus and psi bar is sigma.
Exactly.
You do the trick. You do this trick. Okay.
Yeah. Right. But related. I'm sorry to interrupt, but still related. I'm okay. Maybe not to what Misha asked, but in terms of say. Okay, you are diagonalizing your Hamiltonian matrix, right? And you are talking about the singlet states and non-singlet states. In terms of spectrum, it's kind of, you're implying that it is some certain hierarchy of energies, or it's irrelevant for you.
Oh, this is a very good question. Yeah, for the story today, it's completely irrelevant. It's only about the geometry in the Hilbert space, how the states are orthogonal or not. I'm not including any dynamics, but it would be very interesting to include these errors as dynamical, maybe using some Lindblandian dynamics, then see what happens. In some models, specifically in this BFSS model, which is a dimensional reduction of n equals 4 sub-Young-Mills, to quantum mechanics, then its conjecture, which is motivated by holography and some numerics, then indeed the non-singlets are separated by a finite gap. Yeah, from the.
Okay, but it could be related to n, right, as well.
Sorry.
It could be also going on with n. I mean, this kind of parametrically, it could be, you know, like for example, to be imagine that it is proportional to n in some power. Then you would say, aha, all non-singlet states are far away. No, I mean for the example.
Okay. Yeah, but I don't know any examples with such scaling, but I know an example where it's a finite gap.
Okay. Yeah, because then you have a acceleration in terms of time development, right? I mean.
Okay. Yeah.
Okay.
So let me maybe.
So I would suggest that since we 10 minutes to 1:30, maybe you could show one of the applications, and then people that need to leave can leave, and we remain discussing after that, just to give people a chance to leave if they have to.
Actually, I would say this is my central slide, so everything just follows from that.
Okay.
So in my talk today, I'm just gonna generalize this, first obtaining the appropriate bounds, like this one. And then I'm gonna actually say how state orthogonality is related to quantum error correction. Essentially, you say that all the errors, if the errors are orthogonal, then you can come up in principle with Hermitian operator, and you measure this operator, and it gives you precisely which error occurred, like this one. You measure it, and it tells you which error it is. Is it psi3.1 or psi3.2, psi2.1? And then you can do the correction by acting with the appropriate operators. And then this procedure limited by the fact that if I have too many errors, then orthogonality is not enough. So this is the errors, this is the bounds I obtained. They look a little bit messy because they depend on the number of fermions I have. Specifically, if you look at these bounds, they in fact mean that there's OM. Naively, you would say that if I have operator made of a single operator made of m fermions, then it contains exactly n to the m number of index contractions, and so it scales as n. But I am claiming that it's to the power of 1/10 less. And in fact, these bounds are consistent with the answer in the planar limit or 't Hooft limit, which is this. So usually in the planar limit, you expect that all single traces scale as n, but this is in a different normalizations of psi. So these bounds, they are consistent with the 't Hooft scaling. And to give you an example where it comes from, if you just consider this very simple operator, trace of psi1 to the 4, then you can do a very simple just commutation of psi's. So you take this fermion and you move it to the left, and then you see that everything cancels, and it means that in fact this operator is proportional to identity, and the corresponding factor is n cube. So you see that naively one would expect that this operator scales as n to the 4, but in fact it's n to the cube. And I claim that all these bounds, they are obtained from using obtained from just this operator. And as an example, I can consider this operator psi 1, 2, 3, 4. Here, the upper index is its flavor index. This is different fermionic species. Then I can separate the Hermitian anti-Hermitian part. And then for any operator, there is a very simple inequality, just coming from the fact that this operator is a full square. So I separate the full square. And this way I reduce it to this psi 1, psi 1, psi 2, psi 2. Yeah, and then I can reduce, I can perform this procedure once again. And then I will end up with this trace to the psi to the 4. Yes, these are the bounds I obtained for matrix models. This does not look very impressive, but I used very loose bounds in many cases, and I believe that it can be improved. And as a consistency check, this is consistent with the 't Hooft limit or planar limit.
So in the bulk, what would these bounds correspond to if you had a bulk description of this matrix model?
This is good question. I don't know. This is actually good question to see what kind of dynamical information one can infer from that. So again, for example, with this famous BFSS model, there has been a certain controversy about how exactly the matrix elements scale with n.
Mm-hmm.
And I believe people concluded in the end that they scale like in the planar case.
I see.
So they scale like this, at least simple operators in the ground state. Presumably, this will somehow bound the size of the bulk.
Yeah. Mm-hmm.
So I have 1 minute left.
I think it's okay. You can keep going. Just
I think it's okay to keep going. I mean, if people want to leave, they'll start to leave. But you don't have to rush through everything. Just start but you can start summarizing.
Can I ask a quick question, actually, which may be going to extensions of the work. But do you know whether there's any chance that these ideas can be extended to include like bosonic matrix quantum mechanics?
Yeah, I believe people actually know the appropriate machinery for the infinite dimensional case. It's just I wanted to start from something simple.
Okay.
Okay.
I see. So it's not a problem of principle.
Known,
yeah. Okay. I see. Thank you.
So, okay, maybe let me briefly say how do we describe errors. So if we just have a unitary evolution, it's very boring. I just take a density matrix and multiply it by unitary. If I want system interacting with the environment, then I can do the following. I take a system connected to the environment. Together they undergo a unitary evolution, and then I trace out the environment. And it results in the following evolution, where I have a sum over alpha. So these are E alpha, these are error operators. And so this is a positive operator on the right side, it's good, but I also need a trace preservation. So I also require this. Okay, spin flip. So for unitary operators, dynamics can always be inverted, but in this case, it is not necessarily invertible. So I say that the certain error is invertible if there is another set of operators are alpha, which takes us to the original state.
Yeah, but I'm sorry to add, but when you're saying this condition that sum of the alpha, the degree alpha equal 1, I think that it's the definition of the symmetric cell. You should divide by this sum, right? It's not that you need to put it 1, right? Because you have certain set of unitary metrics, you always can normalize the result by division, right? So it's not like condition on environment, right?
I believe this. So this normalization you're talking about, it will be state dependent. So I just want this to hold for any state, and I'm not allowed to divide the right-hand side. So
okay, but then each E alpha, it is like unitary operator, but different from original one, right? Some unitary operator, right?
Yeah.
So each operator is unitary. So U dagger or E dagger equal 1, right? Okay, now let's say that I have some number of them and each one normalized to 1. Okay, I can divide by number of operators, I mean, to make, at the end, I mean, when I calculate in a tilt, right?
So E alpha, they are not necessarily unitary. For example, in this, maybe I shouldn't have skipped the example. So one of the examples is a spin flip. So I have a spin and I have sigma matrix X. Yeah, and then I say that my spin flip occurs with probability P. Okay. In this case, E1 is just I leave the system alone and don't do anything, and E2 is I act with this X. So this E alpha, they are proportional to unitary, but they're not exactly unitary.
Mm-hmm. I see. Okay. I see. So you are not saying that it's unitary development of different kind. You are saying that it could be whatever, right?
Yeah.
I see.
Specifically in the examples I study, they are proportional to unitaries, but I believe one can study more general things. So as I said, it can be unitary operators can be inverted, but these quantum errors not necessarily. And I say that, okay, it's exactly invertible for certain row or family of row if I can come up with these operators R, which don't depend on row, they depend only on E, such that for any row I can invert it. But it turns out that this is a very strong condition, and one can obtain much better results if one allows like a small error. Then I say that, okay, after the recovery, I don't go to the initial row, but I go close, for example, in the trace distance. So I say that there is like a small epsilon here, and this is the approximate quantum error correction. So now example of erasure, and actually maybe I should have mentioned that actually by acting simply with this non-singlet size, I can correct erasure, which is good. So what is erasure? Suppose I split my Hilbert space into two parts, E and E bar. And then I say that erasure is just when I take a density matrix on this Hilbert space and I map it to and I trace out this subsystem E and I put it in a maximally mixed state. So E is completely lost. It's maximally mixed. No information in E survived. The point is that it can be described using this formalism of error operators E alpha. And E alpha then should be taken as all possible operators supported on this subspace E. So for example, one can check explicitly then if I have one spin, then if I act with equal probability by all possible sigma matrices, then I will end up with a maximally mixed matrix on this on this spin. And then Knill-Laflame condition, it's a generalization of this requirement for error orthogonality. So I say that the following requirement should hold. So I'm saying that E alpha is exactly correctable if I take all my initial signal states to lie in some code subspace. So I have a subspace in the Hilbert space, which I called code subspace. And morally, I say these are signals. And then I require this. So that they projected on the code subspace, the errors are act as identity matrix, and n alpha beta is just a number. So as I said, if I apply just a projector on the singlets on both sides, then in principle I can diagonalize this n alpha beta. It's possible, and I end up with the requirement that the errors are orthogonal. In my case, they will be almost orthogonal, but this is all right, because in this case, I can come up with the syndrome measurement only approximately. Like specifically, the problem boils down of finding the nearest orthogonal basis to this one. So the errors are not orthogonal, but I find the nearest orthogonal basis and measure and make a syndrome measurement for these orthogonalized errors. And this is a very simple linear algebra problem, and it can be solved explicitly by taking the square root of this matrix. So by knowing what the square root of this matrix is, one can bound this epsilon I mentioned earlier. This was done independently by many people. So the main observation is that if all my signals are errors, if all my signals are singlets, then this projection chooses only the singlet channel of the errors. But I will, in principle, when I select only the singlets there, I might have a non-trivial singlet operator, as with this example in the very beginning of psi cubed. But I claim that these are suppressed by 1 over n, and hence this error epsilon is also suppressed by 1 over n. So let me maybe just briefly say the results for the matrix model. Then I will skip the tensor models and then just jump to the conclusion. So this is just a generalization of this example I mentioned in the beginning. I have these SUN generators. So this index in the parentheses, it should be understood as a single index going from 1 to n squared minus 1. And so I have a collection of flavor indices A, and this ij is SUN adjoint. These are equivalent to qubits by Jordan-Wigner transformation, because they have very nice anti-commutation relation. They anti-commute to 1. Actually, unlike these operators. So when I said that this square to 1, I lied to you. These don't square to 1, but these guys do. Here I say that my errors and my erasures can occur in a fixed set. So I just fix the set of indices where the error can occur. It doesn't mean that I know where what error can occur, but I just restrict the set of all possible errors. I'm not saying that error can occur anywhere. I say it can occur anywhere within this set E, and it can be large. Then if I say that erasure occurs, erasure is the most dire kind of error, because it means that I completely erased the subsystem. And in this, from the perspective of this error operators, I just say that, okay, errors operator are all possible operators supported on this subsystem E. So E alpha, these are all possible strings of these operators. So there is a small problem, is that I said that I cannot distinguish, I cannot correct the singlet errors, but also it seems that I cannot correct errors which are conjugate in SUN, because if I take this operator psi1, psi2, with the same index, then one can check explicitly that this won't be suppressed. So in this subsystem E, if I have this psi1, 2 in the parenthesis, this is the adjoint index, I can allow it to be in E only once. So I cannot allow psi2 with the same psi1, 2 in the parenthesis. And so at some point, this procedure should break down when I have too many errors. And precisely it happens because if I have singlets formed from k fermions, this number of singlet operators grows as k factorial. Whereas the suppression, which follows from the bounds I discussed earlier, it's only n to the power of 1 over 10. So it means that this, I can erase no more than n to the power of 1 over 10 fermions, which is still a lot. This is not logarithmic in n, but this is just power of 1 over 10. And when I put everything together, this error is actually quite decent. It's n to the power 2 over 5. So as long as I excluded all fermions with their conjugated indices, and the number of errors is not too big. And this definitely could be improved because I use very loose bounds. My task was to show that the error and this number actually scales with n as some power, because one can be afraid that since the number of singlet operators grows as k factorial, then only logarithm of n errors can be corrected, but in fact it's more. But I believe that it still can be proved. So maybe I will skip the tensor models. Tensor models are nice because there is no, so that like in a nutshell, for many reasons, it's interesting to study psi's in this weird 3 fundamental representation of ON. So this A, B, C, they all go from 1 to n, and each of them is a fundamental in ON. I'll skip all these. One can obtain the bounds similar to the matrix model bounds. Again, one would expect that this O2k would scale as n to the power of 3k, because there are 3k contractions, but it scales much slower, and this is actually important to the relation to the SYK. So these models are related to SYK, and precisely these bounds they have been discussed before in some specific cases. This is not something new.
But in this case, I believe that they do have kind of spectrum, or it's more than not just this, right? I mean, in this tensor model, I mean, and they have this kind of induced gravity, or I mean, so it's or it's. I will listen to a couple of talks by Krepanov, for example. He did not discuss this particular issue you are talking about.
Yeah, he did not discuss error correction. And again, in my case, this particular Hamiltonian, it's not important. Again, I'm just studying the kinematics of the Hilbert space of this psi in the 3 fundamental representation. So this particular Hamiltonian is not important to my story, and specifically this issue he might have discussed is that naively this Hamiltonian, it's also a singlet operator. Naively it scales as n to the 6, but in some relation to the SYK, one needs to show that it scales slower.
But you will have similar statement for SYK as well?
And SYK, so as you probably noticed that in all my talk, I'm talking only about matrix models and tensor models.
Yeah.
SYK, it corresponds to the vector case because fermion has only one index.
Mm-hmm.
And I'm not discussing vectors for a few reasons. First of all, this procedure would not probably work. I believe that the scaling of n coincides with the naive scaling. And secondly, for vector case, there are only few singlets. Mm. So as one of the participants mentioned earlier, when I concentrate on singlets, I cut out a big chunk of the Hilbert space, but for matrix models, it's still big. If I have d fermions, then the total dimension of the Hilbert space is 2 to the power of d times n squared. When I remove all non-singlets, it will be d minus 1, 2 to the d minus 1 times n squared. This is still large because I naively just remove and I have n squared constraints. In vectors model, I have n fields and I have n squared constraints. In general, one is left with just 2 singlets, in fact. So in SYK, it's not good because there are no singlets. And secondly, SYK Hamiltonian is not a singlet. So the SYK spectrum is not necessarily can be classified by representation.
Okay, thanks.
So again, very simple to the matrix model case, one can obtain this bound by cutting and gluing operators. Here it's actually more neat and can be graphically represented. Specifically here I can correct more. I can correct n to the power of 1/6 errors, and there is no bilinear problem because if I have psi and psi, then they form a singlet only if ABC and primed indices coincide. In this case, it's just 1. So there is no problem with this. And the error actually squares as 1/n squared, which is also good. So the summary is that I can, for matrix and tensor models, large n and singlet condition automatically implies correction of non-singlet errors, as long as the number of errors or erasures is not too big. Because erasure is the most drastic error you can imagine. And one can maybe a little bit discouraged by these fractional powers of 1/6 and 1/10, but in fact it's related to the fact that I'm saying that I can reconstruct the original signal completely. Even in this original holographic setup, it wasn't the case, because once I erase A or introduce errors in A, some information in chi A will be damaged. It will be not damaged in the center of the bulk, but near the boundary and in the whole Ka it will be damaged. Whereas in my case, I'm asking a lot. I'm asking that I reconstruct the original signal completely without any losses. So the realistic scenario is that some information is lost after all. And this corresponds to the so-called subsystem quantum erasure correction. It means that errors are no longer orthogonal. In some subspace A, I say that the information in some subspace A might be lost if errors projected on the code subspace does not act as one on this A. So it will be interesting to study this. This is one of the open questions. And in principle, if you want some spatial structure and so on, one can study different vacua in this BFSS model. One can introduce a massive deformation, which is called BMN model. And then this vacua in this model, they in one-to-one correspondence with M2 branes and M5 branes. These are realized as fuzzy spheres. And then one can ask, okay, if I, for example, want to kind of cut out a piece of the fuzzy sphere, is all information lost or not? This is one of the direct applications you can use. Yeah, another question is the singlet erasures, but I believe that for single iterators, it wouldn't be that easy. And all this story I was talking about today, it's actually directly related to these quantum information codes, because in quantum information, the most useful tool to obtain these quantum error correcting codes is so-called stabilizer formalism. You take your spins, all the operators are a combination of sigma matrices, and then you select a certain abelian subgroup of the sigma matrices, and you say that, okay, my signal states, my code states are invariant under these stabilizers. And this is very this looks very similar to this gauge constraint I have been talking about, because I am saying that, okay, my states are annihilated by the charge operators. Yeah, it would be interesting to study this in more detail. And this, maybe someone can correct me, but I believe that all known codes people study are secretly stabilizer codes. So this pairs very neatly with this gauge condition. Yeah, it won't be interesting to study the dynamical aspects, that the fact that typically the non-singlets are separated by a gap in a series with the local bulk. And if there's any way one can extract the dynamical information from these bounds. These bounds, they can be obtained very simple, using very simple combinatorics and algebra, but I haven't seen them in the literature before. And in my paper, in the appendix, I presented a formal proof, and I believe that these bounds, they are consistent with planar limit and some direct computation in these tensor models, and it would be interesting to find some information from them. Okay, this is all I have. Thank you very much.
Hey, thank you. We'll virtually applaud you. If there are any more questions.
You should correct all our errors.
So I actually just have a question on this upper bound. Can you use these bootstrap methods to get an even more precise bound or not? Or is that not relevant here?
I believe, let me see. Well, in the context of multi-matrix models, a bootstrap approach was recently discussed by Henry Lin.
I see.
But I believe in his story, he already studied the planar limit. So, so then the matrix elements are just fixed. Or, yeah, I think. Yeah, I believe, yeah, for at least for one matrix model case, it is clear that there's just single trace operator just scale with n, but I wouldn't be so sure about the multi-matrix models. Mm-hmm. And I believe there was this very neat method suggested by Henry. It's actually very simple. You take multi-matrix model. It's not solvable, but you can write down exact loop equations and then iterate them.
I see.
But for loop equations, they don't determine everything. They need a few basic expectation values, like trace x to the squared, x cubed, trace x4, and so on. And then what he did, he said, okay, all such operators, they should be positive. Their expectation value should be positive. And then one can use the bootstrap approach.
I see, yeah.
in this case and constrain the expectation values of these operators.
Yeah, obviously it wouldn't affect your argument, but it would just tighten the bounds, right? That's all that would happen, right?
Yeah, I believe in some cases it would be
Yeah,
possible to estimate that, yeah.
Yeah.
So hi, nice talk. I have a very naive questions because this is my first exposure to quantum error correction. So in your slides, when you introduce your own work, where you introduce M of those fermionic matrices, and you say they have different upper limit by different choices of k plus 2, k plus 3, something like that.
Oh yeah.
Yeah. Why do I need to? Two questions. One is how large an M I'm allowed to choose? Is that bounded by my requirement of this this n to the 9m over 10 to be smaller than 1?
Yeah, it is. There is a bound.
Yeah.
This exactly n to the 1/4. And it actually one can understand, and I believe this can be improved as well. This n to the 1/4 comes from the fact that, okay, if I have a very long index contraction, yeah, then I contract indices and they all run from 1 to n. But if I have only few indices, it means that this big sum will be dominated by terms where each psi have different indices. So if you have only 2 contractions, you have only 2 indices, and then each of them is from 1 to n. It means that the sum will be overwhelmingly dominated by terms where these 2 indices are different. Yeah, this is kind of a technical statement which allows to the simple derivation of these bounds, because one can with this constraint one can freely just commute psi's past each other without thinking about these extra terms.
And
does this answer your question?
Yeah, helps my understanding. The reason you have to construct the singly fermionic operator is because it's trivial to check if it's non-singlet, the states are the arrow states are orthogonal automatically.
Yeah. So in this particular case, yeah, I have chosen these indices such that they indeed form they can form a singlet. This
right. I'm wondering why do you have to
construct?
Is it because it's trivial? In other cases, they are automatically orthogonal?
Yeah, because essentially they are orthogonal because of the just group theoretic reasons, because you have singlet, and so you must have singlet in the middle.
Sure.
Otherwise, yeah.
Right.
Yeah, this slide actually summarizes everything.
Right.
This Knill-Laflamme condition is just a condition that, okay, the errors, these psi1 and psi2 are orthogonal. And then you see, in order for these states to be orthogonal, one needs to obtain a bound on these guys. Yeah, and you just combine them together, these 2 statements.
Yeah, I was trying to make a connection of these slides to your, holography cartoon pictures, but I couldn't make the mapping of your operation here and the holography picture. Could you say a few more words there?
So in holography, usually these non-singlet operators, they are represented as open strings or folded strings in the bulk. So it means that you introduce a string, and then I guess specifically again in the models with the local bulk, for example, this BFSS, it was argued that these non-singlet excitations, these folded strings, they live near the boundary of the space-time. So it means that you introduce this error, and then it will just always live near the boundary. And so the information stored deep in the bulk will be untouched. So this, in fact, in the BFSS case, it pairs very well with this, with the gravity expectations, yes. But I claim that this holds more generally by just requiring the large N in any matrix model, not necessarily in BFSS, which is very special.
Thanks.
Any more questions?